Hi guys, I'm Prof Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in Kempten in the very south of Bavaria. This is part of my lecture on measurement technology, and today we want to talk about voltage measurement. Last part was about current measurement, and now we want to do the same thing, the same stuff, measuring voltages. Last time, and this will be the same starting point this time, we had a starting point which was somewhat a two-pole source. And again, we want to use that two-pole source because within that circuit we can describe any other circuit containing voltage sources and resistances. So again, what the typical case would be is to measure the voltage along some resistance, which could be the resistance of a motor, for example, again. And now we want to know that voltage which falls along that resistance, which is, for example, a motor, and we would connect our measurement device in parallel to that resistance. So doing so means the voltage which falls along RB will also fall along RM. So the same case, the similar case as before with measuring currents, the same voltage falls along the resistance RB and RM. And so the voltage we are measuring is the same as the voltage along RB. But again, we are doing some error. We are introducing some error. Why we are introducing an error? Because now there's a second route. The current can flow along. That's the first thing. So the current flowing over RB won't be the same, whereas the voltage would be the same. But adding a resistance in parallel will change the added resistance of the system of RB in parallel to RM, and by that the voltage itself will divide into a different ratio than without RM, meaning that the voltage will divide onto Ri and Rb when there's no measurement device, and it will divide in another way when there's this measurement device in parallel on Ri and the parallel connection of RB and RM. So, and that's the error we are introducing again. Okay, talking about the same way as on current measurements, we can just ignore that motor over here. Why? Because we just simply can put it back into that internal resistance. It's somewhat a parallel connection of Ri and Rb over here. And so we only have to look at that system where we want to measure that voltage over here, that voltage without the internal resistance, because that's the voltage we want to know about. And now we have the problem, when we would have a measurement device, a voltage measurement device with a resistance which is, in an ideal case, near infinity, very large. We could be sure the whole voltage would divide onto our resistance of our measurement device, so that the whole voltage would fall along our measurement device. So now for the real case, that's not the case again. And we know that there's some voltage dividing onto Ri and a large part of the voltage dividing onto our internal resistance of the voltage measurement device. So what we want for our measurement device for voltages is to have a very, very large resistance, so that the whole voltage is falling along that resistance. And moreover, when that resistance would be near infinity, it would be like not having a measurement device at all. It would be the same thing as to not connected connectors. Okay, so let's look at the ratio of our wish and our measurement again. So let's just write down the wish, which is our voltage of our voltage source, which can be described as the current over here times the resistance over here. And now our measurement is something different. It's again that current, but now flowing along our internal resistance plus our resistance of our measurement device. Now, doing some ratio between those gives us 1 over 1 plus Ri over Rm without any further calculations. Just insert those relationships into that ratio. And again, we get a graph with a relationship of Ri over Rm and a relationship Rm over Um over UL, some ratio 1 here and some ratio 1 here. We see for a very small ratio in our denominator, we'll start at some small value, going to go through that place where we are 1, which is again 1/2, and go up to 1 at that region, and again we are at some range of 10 to the 2 as ratio between Ri and Rm, which gives us the idea of when or how to think about that errors again. So whenever that ratio is in the range of 1 to 100, 1 to 1000, 1 to 10,000 or something like that, we can, for first glimpse, ignore that additional resistance we are introducing. And in reality, that's often the case because those resistances of typical voltage meters are in the range of 1 mega ohm, 10 mega ohm, or even more. And so the typical resistances within our circuit we are looking at are in the range of kilo ohms, 10 kilo ohms, and so on. And that means we have a ratio which is in favor of our measurement, which allows us to look at our measured values and to assume that they are right. Having said that, there are cases, and there are a lot of cases, where we have resistances in the mega ohm range within the circuit we are looking at. And in that case, we have to deal with that error because we get, as you see over here, real changes, real errors in the range of percentages. So let's calculate that error once more. Let's have a look. So again, we have our error over our, now we have the voltage, our error over our wish, which is the error, which is the measurement minus our wish divided by our wish, which again can be rewritten in that form, which again, without doing the calculations, will result in a ratio for a relative error, which is Ri over Ri plus Rm in percent. And now, as we see, that error will get smaller and smaller with rising resistance in our voltage meter, and will get smaller with falling resistances within our circuit, within our voltage source. Same thing as for the currents beforehand, meaning measuring voltages means using high internal resistances within the voltage meter. Again, we get some problems when not knowing about the circuit because we have unknowns over here, Ri, and unknowns over here, UL. again, the solution is to do 2 measurements with different internal resistances. Again, doing so, we get 2 equations for 2 unknowns, and we can solve those equations to get Ri and UL, whereas UL is the size we want to know about. Again, normally the good voltage meters will provide you with the possibility to change the internal resistance somehow. Again, you could just add a known resistance to in series to your internal resistance of your measurement device to get into that situation. So again, we have everything we need to know about for reality and in the ideal case to remove the error, that systematic error which is introduced by adding that resistance of our measurement device to our system. Okay, if you like that stuff, feel free to subscribe, and in the next part I will give a short overview of how those measuring devices work. Until then, have fun.